contribution of each. It's okay. Better SNR, lower probability of error. And so we're going to try to find a good R that maximizes that signal-to-noise ratio. So then I postulate, well, I don't postulate, but I'm going to ask you to guess, because it shouldn't be too hard, what is the highest signal-to-noise ratio that I could ever hope to achieve in a transmission? I may not be able to achieve it, but I certainly cannot go above it. There would be an upper bound here. Anyone want to try to take a cut at this? I submit that almost after week 1 in the class, you would be able to answer this question. Basic principles. No takers on this one. Okay, let's suppose that the transmission system were such that even though I'm sending messages rapidly in succession, okay, if for each message somehow I could eliminate all of the other messages that came before and after, I would have an optimum detector. I'd be back to the single shot situation. And I know what the optimum detector's performance is for that case. And I could never do any better than that case by having the additional messages just being independent messages. They have no correlation with the current message that I'm transmitting, because I'm trying to do symbol by symbol detector. I'm not trying to get clever, make packets, do other things. I might be able to improve in that case. But if I'm just doing message by message by message, the best thing I could do is if none of the other messages around me disturbed my performance. And that is what we call actually the match filter bound for transmission. And that highest signal to noise ratio, SNR-R, okay, so the maximum over all R's, would have to be less than or equal to, doesn't necessarily have to be equal to, the performance or the signal to noise ratio I would get from my single message optimum detector. And I submit you already know what that is. It's EX bar over N naught over 2, except because the channel's no longer normalized, because I couldn't control the H of F and its gain, so I had a pulse response that changes the energy of the signal by norm p squared. But otherwise, I would have an optimum detector at the point just before and after I add the Gaussian noise, and it would be characterized by this signal to noise ratio, EX bar over N over 2, except my gain changed. The signal power could possibly change in the channel. And I could never do better than this particular number. And this is called the signal to noise ratio matched filter bound. MFB for matched filter bound. If I somehow can design a receiver that has a signal to noise ratio that is very close to this signal to noise ratio matched filter bound, it's not too hard, it's something I put into the R box here. I don't have to worry otherwise about all the optimality I lost, because I'm close to the maximum. So forget all that optimality, just go ahead and design the system. If I'm way off from this bound, well, maybe I have to look a little more closely and say, is there something better, easy that I can do? Do I need to go to a more sophisticated approach? Do I have to go back to the packets? Can I live with what I have? But if I'm close, I'm done. Don't have to go any further. So at least I've got a way to shortcut the whole process. If I can get close on various channels to this situation, I don't have to go through a lot of extra muscle and effort to try to assist the channel. So that's our receiver concept, okay? Couple of things happening here. First big step, signal to noise ratio. If it's high, performance is good. If it's low, performance is not so good. So we're going to use that concept in studying ISI. Second concept, what's the best signal to noise ratio? Match filter bound signal to noise ratio. If I'm close, I'm done. And I have a pretty good design. If I'm not very close, I'll have to figure out whether I could get closer some other way. I'm going to have to work a little bit more completely to analyze the system. All right, so we have that set up, introduction to intersymbol interference and the signal to noise ratio concept. What I would like to do now is we're going to spend the next 15 minutes or so here coming up with a model for the channel. It's a mathematical model that we'll use that tells us about the ISI, tells us about the noise, and we're going to use that to try to construct receivers based on this model. So this model basically starts with the message that was transmitted. Instead of showing separately the basis function, pulse shaping, and cascade with the channel impulse response, I'm simply going to write P of t, the pulse response. And I have additive Gaussian noise. I'm going to call this N sub P of t in this model, just like I called the channel output Yp of t. But I'm going to continue to use the concept of a match filter, as we just saw, and sample at all integer multiples of the symbol period. I've not lost anything in transmission up to that point. I'm going to model at least this section right up to the receiver. Okay. We're going to have models for the receiver also, but we're not quite talking about them yet. So we're just going to try to get the channel part, but I am going to include the match filter and the sampling device in the channel model. And I'm going to define a function. I call it Q of t. And I have to apologize, but we only have 26 letters in the English alphabet, and we have more than 26 quantities in at least in classes like EE 379A and academics and such. So we kind of run out of letters. So we have to reuse them sometimes. Even if we start adding Greek letters, there's only so many of those. And so you get into trouble with this. So this Q of t has nothing to do with the Q function. Okay, so it's going to be defined as phi p of t, that's just the pulse response divided by its norm, convolved with the match filter. Okay, so it's basically the pulse response convolved with itself reversed in time, and we normalize that, okay, for both of the filters. Some people call this an autocorrelation function for the channel. That would be okay. It has all the properties of an autocorrelation function. It would suffice if you had some random variable somewhere and you said this was random process and you said this was its autocorrelation function. If it was stationary, you'd be okay to go ahead and do that. What happens here in this particular definition is it has a very nice property. Q of 0, which means the function Q evaluated at argument 0 as a nice value that I submit is easy to see what it is. Any takers on this? If I take a filter that's normalized, convolve it with itself reversed in time, and stick in 0 for the time at which I evaluate the convolution, you'll see inside the integral that you got the squared norm of the filter. Okay, and we know that's 1 because all these filters are normalized. So this is 1. Kind of nice property to have, because what it means is that a message at time k going through the channel, which has a cascaded response of Q of t, is going to appear over here, at least in terms of the contribution of Q with the same amplitude. So we could expect to see an output which includes xk plus some other stuff from all the other messages and from the noise. So this particular model has no gain in effect in it because I've normalized the match filter in the receiver. It's also perhaps obvious, and you can check this, that Q of minus t is equal to Q star of t. This is called Hermitian symmetry, and it's something that has to be true for any autocorrelation function, or for that matter, any function convolved with itself reversed in time. And what that means is that Q of omega, the Fourier transform of Q, has to be greater than or equal to 0. And it's also real This is sometimes called a positive real function. They take the Fourier transform. Even though we got complex signals involved here, the Fourier transform of this Q of omega is real and non-negative at every single frequency, positive, negative, or otherwise. Okay, so that's kind of a nice function. We're going to use this Q of t to basically characterize the intersymbol interference in the channel. Y of t, the output of the match filter before it's sampled, I forgot to write it here, there's Y of t over here, is going to be equal to, well, let's look at this. I've got P here, and I've got Q of t throughout the channel. So I could actually write this as the sum over all k of x of k times q of t minus kt, except I don't quite have q. I don't have phi p of here. I've got p of t, which has a gain of p out in front. And I've got the gain in the channel times each of the messages times q of t minus kt, plus the noise involved with the match filter. So that is my channel output. Okay. From here through here is basically norm p q, and I've got the messages x of k exciting the system. So this is the sum of the responses for that linear system to each of those messages, and that's the filtered noise at the output. I'm going to call this noise n of t. And I submit we know how to deal with this noise. If this is additive white Gaussian noise here, we just ran through a match filter that was normalized. And we all know at this point that if I take white noise through any normalized filter, its variance at each sample time is n naught over 2, right? Because that's the basic result we had from chapter 1. So the variance of this noise is going to be E of nk squared. I should really put magnitude because it could be complex noise, but that's going to be n naught over 2. If it's complex noise, I better put a bar on that, divide by the number of dimensions. Okay, so if I sample the system at all of the time instants, I got yk is equal to norm p times the sum over k, x of k, and I shouldn't, at the output of the channel, I shouldn't use k here if I've got sampling. I should use a different index on the sum, m, so we'll write this as x of m times q of kt minus mt plus n of kt over here. Now this quantity we're going to abbreviate q of k minus m. So it becomes a discrete type of function because we've sampled, and essentially those are the samples of the original function q of t. So what I really have is norm p times x of k convolved with q of k plus n sub k. And I know each and every sample of that per dimension has variance n naught over 2. I've got xk here filtered. So it's not quite the message I want. I have the intersymbol interference, and that will be completely characterized other than the simple gain factor here by q of k. So that's why I defined q of k here. I got a single function that's going to characterize the intersymbol interference. Now I could actually write the output yk as equal to norm p times x of k by itself plus the sum for m not equal to k of xm q of k minus m plus n sub k. And this is essentially the message. That's what I want. It's been scaled by the gain of the channel. Gain of the channel is bigger than 1. That's great. Got a little higher signal to noise ratio. If it's less than 1, I lost some signal energy in passing through the channel. This is the ISI. And the contribution of all the other messages is going to be characterized by that function Q. And of course, this is filtered noise, filtered by the match filter. And all of this is the distortion in the system. Now, it's not quite E sub k because I've got a gain factor here in my original model. If I did nothing in a receiver, okay, I wouldn't quite have xk at the output of the channel. I'd have to divide by norm p. But if I took this second term here and I had no receiver, R was essentially passed through, go directly to symbol by symbol detector and decide, then if I divided by norm p, I'd have the signal E sub k that we were talking about earlier. So I've got message and distortion. Distortion decomposes into an inter-symbol interference component and a noise component. Okay, so, and we could lastly write this in terms of Z or D transforms. I like to use D transforms because anywhere you look in communications, you won't see Z used in transmission. And there are a lot of reasons for that. Some of them just date to the communications people using the concept earlier. But D, if you've taken a basic circuits class, digital flip-flops, they have a D flip-flop. That means a delay. Okay. Now that started in the communications world basically, and so a lot of the original work uses D. Maybe it's a little more convenient mathematically to use Z inverse instead of D. But if you want to change back and forth from your DSP class to your communications, that's all you need to do. Anything that was happening inside the unit circle in the Z transform is now happening outside the unit circle in communications and vice versa. Okay, but that's the only change. But you're better off getting a familiarity with D because the industry uses D, not Z inverse, in terms of characterization of systems. So knowing that Z transforms or equivalently D transforms multiply Y of D is equal to X of D times Q of D times norm P, the gain, plus N of D. And if you wanted to get a discrete, if you want to get a Fourier transform of the sequence, you could stick in D equal e to the minus j omega t, where t is the symbol rate, and you would get the Fourier transform representation of the channel. Okay, so we have a model of the channel. Okay, we have to find Q. We've got one function other than a gain factor, norm P, that's characterizing everything. So first thing we would do in analyzing a channel is find Q. Once we have Q, we can begin to work with the channel, try to assess it in terms of different receiver structures, how bad it would be if we didn't use a receiver at all. Do we need to use one? Now I have an example in the notes, figure 3.9 that you can look at, which is basically an example of some inter-symbol interference. But what happens is you get a function there. When I'm more interested, here in class today, you can look at it. There's a nice shaping, but it's kind of like squashing pulses together, and you get inter-symbol interference for a channel. This particular channel is not perfect, and the Q sub k values are 0 except for 5 entries. 1159.2029, 1.2029 minus 0.1159. Now that particular channel is a baseband channel. It's real. It doesn't have any complex entities in it. Now we can look at the function, look at it in the time domain, say, okay, looks good, looks bad. But what I can test is the thing that's really important is these 5 samples. It's 0 outside of this range. What is this telling me? Well, we always know the middle sample's got to be 1. Okay, because that's one of the properties of this Q of t. But also what it's telling me, if I know my message gets through with amplitude 1, that the message just before and just after have about a 20% contribution. Okay. Not as big as I am getting through the channel, but they're there. I can clearly see them. Now if I go one message further away, it's decaying, it's down to about 10%. And if I'm 3 messages or 4 messages or 5 messages away, I'm too far away, I can't see it. So that the intersymbol interference is basically confined to 2 adjacent values, either before or after. And so what I would like to do is say, okay, what might we think about this in terms of intersymbol interference? What's your gut reaction on this? You go, well, that's 20% down, 1 message away, 10% down, 2 messages away. I mean, my gut reaction, without knowing, of course, in this example, where we're headed, is that this wouldn't be too bad. It's only 1/5 the size away. You know, I've got to have opposite sign for it to really hurt me anyway. And you know, is this a big deal? Well, it doesn't look too bad. Only a few samples contributing. But what we're going to see is that just this